Put a hot dog next to a hamburger. One is long, thin, and built to slide through without resistance. The other is wide, dense, and built to carry real weight. 0W-20 is the hot dog. 5W-30 is the hamburger. And the choice between them is not a preference question. It is an engineering question, and the engine already answered it before you ever walked into the parts store. Most drivers pick motor oil the same way they would pick between those two options at a barbecue: habit, price, or whatever the shelf had in stock. That approach works fine until the wrong viscosity grade goes into the wrong engine. The consequences of that mistake come in the form of either a warranty denial or a bearing failure, depending on which direction you got it wrong. The number on the front of the bottle is not a quality score. It is a behavioral description. 0W-20 does not mean the oil protects less than 5W-30. It means the oil behaves differently at different temperatures, and the engineer who designed your engine chose that specific behavior on purpose. The letter W stands for winter. The number before it describes how the oil flows during a cold start, before the engine reaches operating temperature. A lower W rating means the oil reaches cold bearings faster when the engine first fires. That first few seconds of cold start operation is where the majority of engine wear accumulates over a lifetime of driving. The bearing journals are dry of pressure. The clearances are at their widest from thermal contraction, and the oil pump is building flow from a cold, sluggish reservoir. 0W oil clears those passages faster than 5W oil does. And that speed difference is not trivial at the microscopic level of a bearing, running without a full hydrodynamic wedge. The number after the W is the operating viscosity at running temperature. 20 means thinner when the engine is hot. 30 means thicker. And the gap between those two hot viscosities, measured under the conditions that actually occur inside a loaded engine, is what the high temperature, high shear rating captures. 0W-20. Oil is a direct product of corporate average fuel economy regulations. The federal government mandates a fleet average fuel economy target across every vehicle a manufacturer sells. Missing that target triggers per-vehicle fines that compound across an entire model year's production run. One of the most efficient ways to reduce fuel consumption without redesigning an engine from scratch is to reduce the drag the oil itself creates. Oil is resistance. When the crankshaft spins through the crankcase, the oil clinging to rotating components acts as a hydraulic force that the engine has to fight on every revolution. Thinner oil at operating temperature means less of that internal resistance. Less resistance means more of the combustion energy goes into moving the vehicle forward instead of generating heat from fighting thick liquid. Real-world testing has shown measurable improvement in fuel economy when modern engines run 0W-20 instead of 5W-30, which is exactly why Toyota, Honda, and Hyundai mandated thinner grades across their passenger car lines as those regulations tightened. The engineering decision runs deeper than fuel economy compliance, though. Modern engines designed around 0W-20 do not necessarily have narrower bearing clearances than the generation before them. What changed is the surface finish quality and the oil pump architecture. Mirror smooth surface finishes machined to tighter eccentricity tolerances allow a thinner oil film to maintain full separation without contacting metal asperities at the peaks. Variable displacement oil pumps are engineered around the flow physics of thin oil, delivering high volume efficiently at the lower viscosity those surfaces are designed to operate on. The oil galleries feeding the variable valve timing actuators in a modern Toyota or Honda rely on that high-flow thin oil to keep hydraulic phaser response fast. A thicker oil at the same pump pressure delivers less volume through those galleries per second. Less volume to a hydraulically actuated camshaft timing system means sluggish phaser response and delayed timing corrections. While it might not instantly throw a check engine light, you are forcing the system to operate outside its engineered hydraulic window. The engine was built for the hot dog. 5W-30 exists because some engines and some operating conditions generate stresses that thin oil physically cannot survive without a measurable cost. High temperature, high shear viscosity is measured in centipoise using an industry standard test run at 150 degrees Celsius under a shear rate that simulates the conditions between a crankshaft journal and a bearing shell underload. This measurement is not the same as kinematic viscosity measured at room temperature. An oil can appear thick in the bottle and shear down to a fraction of that apparent thickness when squeezed between two metal surfaces moving at high speed. The high temperature, high shear rating is the number that describes what the oil is actually doing at the critical interface, not what it looks like on the shelf. 0W-20 oils carry a minimum high temperature, high shear rating of 2.6 centipoise under the current American Petroleum Institute service specification. A heavy-duty 5W-30 built to European performance standards can push that to 3.5 centipoise. That is a 35% increase in fluid film thickness under extreme load. Under the weight of a towing application, that margin is the distance between a bearing that holds and a bearing that starts leaving metal. When a truck pulls a loaded trailer up a grade, the connecting rod bearings and main crankshaft bearings are carrying combustion loads and inertia forces simultaneously. The oil film between the journal and the bearing shell has to maintain a physical separation between those metal surfaces on every power stroke. A film that shears down to 2.6 centipoise under that load is a thinner physical margin than a film holding at 3.5. That 35% gap in fluid film strength at peak combustion load is the distance between full hydrodynamic lubrication and bearing contact that starts showing up as elevated metal readings in an oil analysis. That is why every manufacturer rating a vehicle for heavy towing specifies 5W-30 at minimum, and many step to 5W-40 or 15W-40 for sustained severe duty. The Hamburger has density because the table it was designed for is heavy. Putting 5W-30 into a modern engine that specifies 0W-20 is not extra protection. A thicker oil changes the hydraulic behavior of a lubrication system engineered around high-flow thin oil. Variable valve timing phasor response slows because volume delivered to the actuators per second drops. Cold start lubrication lags because thicker oil takes longer to prime a system built for fast-moving thin oil. The fuel economy the engineering team designed into that platform drops along with the correct viscosity. The reverse error is more expensive. Running 0W-20 in an engine designed for 5W-30 means the oil film under towing stress or sustained boost pressure is thinner than the bearing clearances were machined to tolerate. Wear accumulates silently. An oil analysis starts showing iron readings climbing over successive intervals. By the time a bearing shows distress symptoms, the cumulative damage from running underspecified oil through hundreds of hours of real load is already baked into the metal. The hot dog is engineered for passage speed, precision surface finishes, and fuel efficiency in a platform designed around it. The Hamburger is engineered for density, sustained film strength, and the bearing loads that come with real work. Neither one is a better oil in isolation. Each one is the correct oil for a different machine, and the machine already made the decision. Read the viscosity specification in the owner's manual. Match it exactly. The number on the bottle is not a preference and it is not a suggestion. It is what the engineers calculated the engine needs to survive the clearances they machined into it.